You are currently sharing screen. Please go ahead.
As shown in the slide, video editing conducted by T2I and T2V LDMs without the integration of FLDMs shows distinct drawbacks. T2I LDMs, although adapted in frame-wise editing, tend to cause flickering issues. The tree in the background has obvious shape changes across frames. Similarly, T2V LDMs, despite their ability to maintain temporal consistency, often compromise on structure quality. For example, the shape of the car is different from the original car. Since the first row, FLDMs address these issues by fusing the latency of both T2I and T2V LDMs during the denoising process. As the denoising time step progress, there is an improvement in both the structure integrity and temporal consistency of the video edited.
Sorry for interrupting. Can you share screen?
Okay.
Yes. It's not connected. Yeah, I think it works now. Thank you.
Okay. Here is the architecture of FLDM. Given the source video and a target prompt, the VE encoder compresses the input video into a clean latent. Then we apply DDIM inversion with T2V and T2I LDMs to invert the clean latent into noisy latent. Then we use the T2V and T2I LDMs to predict noise. The T2I model predicts noisy frame by frame, and the denoised T2I latents are concocted at the temporal dimensions. Then we apply latent fusion by combining the denoised latents from T2V and T2I models. So a mixed noisy latent is generated for the next denoising time step. The hyperparameter alpha controls the ratio of T2V and T2I latents. A larger alpha ensures a better temporal consistency but does harm to structure and text alignment. If the alpha is too small, it would degrade to frame-wise editing with T2I model. In practice, we notice that fusing multiple latents at the early diffusion step results in noisy output. So we let T2V and T2I models infer separately in early tau steps and perform latent fusion at afterward steps. In addition, we propose an updated schedule for the fusion ratio. The ratio is incremental increased after each latent fusion steps. Our method can work for latent diffusion models within the same latent space. We choose VRD-RD and zero scope for T2V models, and control net and instruct pixel to pixel for T2I models. Specifically, the temporal modeling of T2V models affect the temporal consistency, and T2I models affect spatial structure. Next, we will show the editing result of our methods. Here is our video editing results. Our method can edit object, background, and style of the video. We present the effects of fusing T2I models with VRD-RD. In the case of golden fish, instruct pixel to pixel has good capability of frame editing, but lack consistency between frames. Video generated by VRD-RD individually have decent temporal consistency, but lack original structure. When applying FLDM to VRD-RD and instruct pixel to pixel, both temporal consistency and structure integrity can be improved. In conclusion, our method contribute are summarized and follows. We propose multi-source latent fusion, a method that can seamlessly integrate of the shell T2I diffusion model with T2V diffusion models. To the best of our knowledge, this work is the first to review that T2I and T2V diffusion model can complement each other effectively, especially T2I models are essential for providing structure integrity, while T2V models are important for ensure temporal consistency. Unfortunately, the authors team could not attend the conference in person. I'm presenting the work on their behalf and may not be able to effectively handle the QA section. Thank you for your attention and understanding.
Thank you for your presentation. And now,
Hello, I'm Yu Chao from National University of Singapore, and I will present video swap. And this work is together worked with peers in Manta. Let's first describe the problem of video swap. I name it as a customized video subject swapping. That's given a source video and given several a reference image of a target concept. We need to swap the foreground concept to the target one, and we also need to preserve the background same with the source video. And the video swap is a video editing problem, and the key research problem in video editing is how to extract motion from source video and then transfer to the target edit. The pioneer work to a video implicitly encode motion in model weights by fine-tuning from the source video. Although we have the flexibility in subject change, the temporal consistency is not very good. And then the following works in video editing investigate different dense correspondence to achieve better temporal consistency. For example, the phase zero use the attention map, and the re-render video use optical flow and edge map, and the stable video use the deformation field. All those work use the dense correspondence, and we can see the temporal consistency is keep improving. But the problem is it will impose a strict shape constraint. For example, in re-render video, it uses the optical flow and edge map. So the swap result is need to conform the shape of the source concept, but it cannot reveal the target shape of the target swap. And in our work, we try to think if the dense correspondence need to residual shape, so can we use some sparse correspondence to enable the shape change and also align the motion trajectory from the source video? So we investigate a sparse semantic point as correspondence in order to shape change video editing. And this is motivated by some related work. One is the diffusion model feature. They find that the diffusion model feature have a robust semantic point correspondence. That's when you query a point in the source image, and even if have a large semantic change, the the point correspondence can be achieved by the diffusion feature directly. And another serious work is check any points. It is a newfound problem to perform long-range trajectory estimation in a video. And then is image customization, mix of show, and it can use several images to encode the concept identity and maintain the similar inference behavior to the pre-trained diffusion model. And the challenge use the semantic point as correspondence is unlike the low-level correspondence like age or depth we can extract from all videos. The semantic point vary with a different open world concept. So the question is, can we learn the semantic point control for a specific video video subject using only a small number of the source video frame? To verify this problem, we designed a toy experiment as we define a set of semantic points, and we annotate the semantic point on 8 frames from the source video to form the training pairs. And we optimize this using a T2I adapter one control net like architecture that we find the semantic point optimized on the source video frames have the potential to align the subject motion trajectory that we can drag the points to perform the key point alignment. And also we can use this to change the shape. And also the semantic points have a robust transferability across semantic and low-level changes. So based on the 2 observations, we aim to introduce video swap to exploit the potential of semantic point correspondence and also reduce the human intervention to annotate semantic point or drag the points. And here's the overview of our video swap framework. We can see it is a typical design of a video editing that we first inversion to the DDIM noise space and then decode to and then perform sample diffusion steps. And the main contribution is when sampling, we inject the semantic point correspondence to the units and then use to guide the motion trajectory. And here's the framework of a video swap. First, we need to extract the motion trajectory from the source video that we given annotation of human key points at the keyframe, and then we use the track any point like a co-tracker to get the trajectory along the whole videos. And we now get the point trajectory from the source video. And from the point trajectory, we average the semantic embedding. For each point, we use the diffusion feature to get this semantic embedding, and we average from all frames to get the semantic point embedding. And given the trajectory and the embedding, we use this to optimize on the source video to register these points as a control points. We use learnable MLPs to project it to the multi-resolution and inject it to the diffusion models and tune from source video. And based on the tuned control points, we can perform several editing. We identify 3 typical type of the point correspondence. The first is one-to-one point correspondence. That's the source concept and the target concept have similar semantics, and the source video control points can be directly transferred to a target. But for the second is we only have a partial point correspondence. Like for example, we want to swap an airplane to a helicopter. The helicopter usually don't have wings, so we can remove some control points on the wings to perform the shape change. And then the final is the point correspondence with shape morphing. That we need to drag some points, and we can perform the more large shape change. And the drag points is supported by the canonical space, because the drag points at the key frame is straightforward, but propagating the drag displacement over time is non-trivial. So we need to design a method to robotics propagate the point displacement to all video. So we resort to the canonical space formed by their neural atlas. That's we can drag on the keyframe, and the drag displacement is first project to the canonical space, then propagate to the all video frames. And based on this drag, we can perform some large shape change. For example, the source correspondence is tracked from the source video. Then we can drag to then we can drag based on the target concept, and then we can use the same trajectory but change the shape to perform the shape change. And here's some results of our video subject swapping on objects. We can see it can swap to some large shape change, but keep the trajectory same with the source video. And here's some transfer in animal, some non-rigid motion. And we can also perform on human concept. For example, we can use to swap the character in the source video. Compared to previous work, we can see the most of previous work work on the shape preserving editing, that we need to keep the shape same with the source video, and our work it can work on the shape change once, but also with the same trajectory with the source video. And compare some our build baseline on video diffusion model, we can see the previous correspondence, the low level correspondence like depths. It also have a shape constraint, and they cannot use to guide the non-rigid motion. And our methods can guide the motion and perform the and support the shape change. So our code is released at you can scan this QR code for the code release, and our poster at June 19 Wednesday. And welcome to drop by and chat further. Yeah. Do you have any questions?
Now is the QA session, so if anyone has questions, please raise your hand. Maybe let's move on to another keynote, which is
Hello. Okay. So hello everyone. My name is Ziqi Huang. I'm currently a PhD student from MM Lab at NTU, and I've been working on visual generation, like image and video generation, and the evaluation of such visual synthesis models. And today I'm happy to take the next 10 to 15 minutes to do a sharing on VBench, which is a comprehensive benchmark suite for video generation models. So video generation has been developing really fast over the past 1 or 2 years. This is not an exhaustive list, but the yellow circles show some very representative image generation models, and the blue circles are the video generation models. So we see that with the recent advancement of image generation and techniques like diffusion models, many video generation models actually follows along, and they have become like bigger model size, and they gradually become to possess the capability of generating general videos given arbitrary user-provided text prompts. So with so many video generation models available, a natural question is how to evaluate these models or what's each video generation model good at or bad at. And if we take a look at some existing evaluation metrics, for example, the very widely adopted FVD, it has been widely adopted, but there are some problems. For example, FVD is only a single number, and a single number is not able to tell us like the individual model's strengths and weakness. And also there has been some studies showing that metrics like FID and FVD, they are not perfectly aligned with human perception and has their own problems in terms of like bias and detailed processing. There's another line of works, video quality assessment. This line of works is targeted for evaluating videos, but they mainly focus on the artifacts in user-provided contents. For example, like the distortion or compression artifacts in videos, for example, captured by mobile phone. And we really want some ways to evaluate video generation models, which has multiple dimensions to provide very detailed feedback and aligned with human perception, and also focusing on some artifacts specifically in AIGC, like in the generated content. And therefore, we are motivated to propose VBench in order to comprehensively benchmark and evaluate all these video generative models. So here is an overview of VBench. First of all, we have a comprehensive evaluation dimension suite. That means we break down the concept of video generation quality into many ability dimensions. And for each dimension, each ability dimension, we have a prompt suite, which is a list of text prompts. And from these text prompts, we sample videos from several open source video generation models. And then using these videos, we perform evaluation using the method we developed for that particular dimension. And we also invite a lot of human annotators to do preference annotation on these videos. And we conduct this process iteratively to make sure that the evaluation method we developed for that dimension is well aligned with human perception. So that's the overview of VBench. And the first part is the dimension suite. So we have 16 ability dimensions in total. First of all, we break down the grand notion of video generation quality into two aspects. One is video quality, which considers the video itself instead of like whether it's aligned with the user-provided text prompt. And the second part is video condition consistency. That means whether the video is aligned with what the user wants. Is it following the text prompt that the user provides, or is it following the image that the user provides? So under these two broad dimensions, we further break it down in a hierarchical, fine-grained, and relatively disentangled manner. For example, for video quality itself, it's further break down into temporal quality, which considers like the quality in the temporal dimension between video frames, and the frame-wise quality, which means the quality within a single video frame. And with these 16 ability dimensions, each dimension focuses on assessing one aspect of video generation quality. So it's like we are breaking down the difficult task of video generation assessment into several subtasks. As for why multiple dimensions are needed, first, as we mentioned earlier in the motivation, if we have multiple dimensions, then we are able to provide feedback on individual models' strengths and weakness. For example, some models can be good at like generating videos with a very good subject consistency or background consistency, but might suffer a little bit in terms of dynamic degree. For example, their degree of motion, the motion is not very large. However, some other model could be really excellent in generating very aesthetic, appealing video frames, like with very good aesthetic quality, but the temporal quality might be their drawbacks. So in this way, evaluating in multiple dimensions, we will have a better understanding, like whether this is a good temporal quality model or this is a good frame-wise quality model. This provides more insights. And the second reason is that different people can prioritize different ability dimension differently. For example, based on the application, if the user wants to use the model for, let's say, AI-aided design to give them some inspirations, then they don't have to have super good video quality. However, they kind of like the video to follow their text prompt to give them what they want exactly. And on the other hand, if the application is, for example, advertisement generation, then perhaps the frame-wise. Okay. Wait. Hello.
Sorry, on.
I think this one is. Hello, no, this one is working. Okay. Okay, so I was talking about if, for example, the application case is advertisement generation, then perhaps the temporal quality is very important because we don't want the final advertisement product looks temporally inconsistent, and the aesthetic quality is also very important. So which dimension is important? This really depends on the application and the individual user. Okay, and here example of a particular dimension. Under temporal quality, we have a dimension called motion smoothness. So in this dimension, VBench provides a numerical number as the final result between 0 and 1. So a higher score indicates relatively better results in terms of motion smoothness. And we do this for every 16 dimension. Okay, so the second part is the prompt suite. It's natural that we want a very diverse and comprehensive prompt suite, a list of very diverse text prompts in order to cover as many types of content as possible. This is very natural, but on the other hand, we also want a very compact prompt suite. Because different from evaluation for some other tasks in perception or LLM, where the model inference is quite fast. In video generation, sampling of diffusion models nowadays can take like a few minutes for one single sample. So we need to like take care of the evaluation efficiency. Therefore, we need to control the total number of prompts for each dimension. And other than prompts for each dimension, we also have a prompt list for different content categories. For example, we have prompts for animals, for food, and for human, and for plants and vehicles. And we will touch on this in a minute. And considering the diversity and compactness concerns, let me try to close this one. Sorry, just give me 1 minute. Perhaps I can exit the slides and re-enter again. Okay, Ken, sorry about the interruption. So we have around 100 prompts for each ability dimension, and we also have around 100 prompts for each content category. So I talked about just now, VBench, we value human alignment a lot. And for each evaluation dimension, we repeat this process of human alignment. We pass all the generated videos to human preference annotation, as well as the current iteration of our method in development. And we make sure that the results from both sides are well aligned together. And actually, this is the most time-consuming part during the development of VBench. Here are some evaluation results. So this radar chart shows some relatively state-of-the-art text-to-video generation models. And there could be a lot of information to interpret from this radar chart. But one interesting thing is if we look at here, you might notice that there's a missing corner in this dimension called dynamic degree. And what dynamic degree means is the strength of motion, or whether the motion is large or not. So we discovered that there exists some kind of trade-off between all the temporal consistency dimensions and dynamic degree. And this kind of trade-off exists in almost all the models before Sora. So we also believe that it's important to evaluate not only temporal consistency, but dynamic degree as well at the same time, because improving either one of them doesn't necessarily indicate the improvement in temporal quality. And VBench has been holding a leaderboard. As of now, we have for actually 15 text-to-video models and 12 image-to-video models on our leaderboard. And if you are working on a video generation models, you are welcome to join our leaderboard. We also done some little experiments on comparing video and image generation models. And we find that there is a relatively huge gap in terms of compositionality. That means image generation models, they are generally better in terms of composing multiple objects, or making an orange to be on the left-hand side of an apple. So there's still a huge gap in terms of compositionality comparing to other dimensions. And also we did the evaluation across different content categories. So here content category is different from ability dimensions, which refers to types like animals, food, and scenery. And we discovered something interesting. For example, here for the model Cop video, it's aesthetic quality. Actually, the overall aesthetic quality of Cop video is not so good comparing to other more recent SOTA T2V models. However, we discovered that it actually achieves quite nice aesthetic quality in the food category. That can imply that Cop video actually has the potential to achieve relatively high aesthetic quality, at least in some particular category. And perhaps with more careful data and training strategy choices, we can improve this model aesthetic quality in terms of other content categories. And therefore, we also recommend evaluating video generation models, not only based on ability dimensions, but also consider different content categories. In this way, we can better uncover the hidden potential of different models. And it's also give us more informed decision when we decide like what's next iteration of data set we want to use. VBench is fully open source, including our evaluation method for all the 16 dimensions and the prompt suites. We are also releasing, we have already released our human preference annotations on all the sampled videos. And we also organize the sampled videos used in our evaluation and release those videos on our GitHub. And now you can simply install VBench and run it using some simple commands. And there has been some serial works in progress, for example, evaluating image to video models, evaluating longer models, and also evaluating the non-technical aspects, like the trustworthiness of generative models, like the culture, bias, and safety. And there has also been some amazing concurrent works in video generation evaluation. And we believe this field of evaluating visual generation is still open for dialogue and discussion, and we are collecting a list of papers to witness this development of this direction. And VBench wouldn't be possible without the team of wonderful collaborators and teammates. So with that, I would like to end my sharing, and I'm happy to take any question. And we are having a poster session this Friday morning. Also welcome any question or discussions over the poster session. Thank you.
Thank you so much, Ziqi, for your presentation of VBench. If anybody has questions, please step ahead or raise your hand. Or maybe out of curiosity, I have a personal question.
Yeah, sure.
Recently, there are some very brand new video benchmarks, such as like video MME or so. So how do you think the relationship of those benchmarks with VBench? Are they complementary or orthogonal?
I believe it depends on the types of benchmark. If, for example, VBench is following a multi-dimensional approach to evaluate the quality of video generation. And I believe most works into this direction, like designing multiple dimensions to evaluate video generation, then it might be complementary, because the 16 dimension of VBench, although they are carefully designed, they might not be the ultimate perfect answer to dividing the concept of video generation. However, there are some other line of works which takes a different approach, I believe, like, for example, the T2V score work. I think they provide a final score towards the video generation quality. And I think their line of works is kind of orthogonal to the road that VBench is taking.
Thank you.
Yeah, any other questions? I'm also happy to take over the poster session on Friday morning.
Great. So thanks, Ziqi. I think, and thanks everyone for attending. I think we are going to wrap up the workshop